Okay, hello and welcome back to Chemistry Talk. Today I'll be introducing kinetics, some of the theory behind kinetics, and a little bit of math, but in future videos we'll be doing more of the math with kinetics. So in kinetics, we're studying the rate at which a chemical reaction occurs. So a chemical process will go to completion in a certain amount of time. You can observe this in a lab by um, seeing when a precipitate forms or how long it takes for a gas to form, and that is an indication of how quickly the reaction's occurring. Now, in kinetics, we also study something called the reaction mechanism. What's causing this reaction to occur? Is there a catalyst? What ions are reacting with each other to cause this reaction to go to completion? So that's the study of the reaction mechanism. Now, when we're talking about reaction rate, how fast a reaction occurs, there's four main factors that affect this reaction rate. Now, there is one other factor that has to do with the type of substance, but the four main factors that we study in kinetics are the physical state of the reactants, the concentration of the reactants, temperature, and the presence of a catalyst. Now, a lot of this is based off of a theory that's studied a lot in chemistry, particularly when you're looking at how molecules interact, and it's known as the kinetic molecular theory. Now, the kinetic molecular theory, in brief, states that when temperature is increased, molecule collisions are going to increase. That gives the molecules more energy because they're bouncing off of each other more, and that would increase the rate of a reaction. So when we're looking at how the physical state of reactants affect the reaction rate, we're looking at how molecules come in contact with each other. When molecules come in contact with each other, you start to get a reaction. And when the reaction mixture is more homogeneous, meaning they're more similar like in chemical composition, the reaction can go to completion faster. This is also to say with the concentrations of the reactants. When you increase the concentration of reactants, you're going to increase the chance that those molecules will collide. It's more concentrated. So the molecules will collide more quickly. That will increase the reaction rate. Temperature is also a very important part of reaction rate. At higher temperatures, the reactant molecules are going to be colliding more and have more kinetic energy. They're going to move faster and the reaction is going to move faster. Now, all of these can have an inverse effect. If you were to make the physical state of reactants more heterogeneous, more different in chemical composition, the reaction will slow down. If you decrease the concentration of the reactants, the reaction will occur slower. And if you decrease the temperature of the reaction chamber, you're going to decrease the rate that the reaction occurs. So they all are related proportionally. Now, the last one is the presence of a catalyst. And catalysts speed up a reaction by changing the mechanism. Now, how they change the mechanism of the reaction is by lowering the activation energy. So I'm not sure why that graph went up there, but catalysts are consumed during a reaction. And when the reaction is over, they're not going to be chemically changed. They'll be back to their original state. Catalysts work to speed up a reaction by lowering the activation of the energy. Therefore, you're increasing the rate at which that reaction occurs. So if you look at this graph here, you can see that this black line here represents a reaction that occurs without a catalyst. A lot of energy is required to get it up to this point where the reaction starts to occur. But if I add a catalyst, the reaction occurs much quicker. It starts down here versus all the way up here because you're lowering the activation energy. So you're looking at a reaction that occurs without a catalyst. It takes this long to get the reaction to occur. I'll call that X, but when you have a catalyst, it would only take this amount to occur, Y. So you're lowering the activation energy, the reaction is going to happen more quickly. So rates of reactions can be determined by monitoring the change in the concentration of reactants or products. So I have an example reaction here. I'm combining butyl chloride with water and I am forming butyl hydroxide and hydrochloric acid. And what I've done is I made a data table of the time in seconds and the concentration of butyl chloride at that time. So while I can study the change in butyl chloride concentration, the average rate of reaction will change. Now, the average rate of a reaction is the change in the concentration in the reactant that you're studying divided by the change in time. So here at 0 seconds, I'm starting with a 0.1 molar butyl chloride, but at 50 seconds, the concentrations decreased to 0.0905 molarity. So, if I wanted to calculate the average rate of reaction in this interval, I would take my initial concentration minus the final concentration, and I would divide it by the change in time over that interval. So the change in time is just 50 seconds. So we find that the average rate of the reaction would equal 1.9 times 10 to the negative fourth, and this unit, when you're looking at reaction rates, is in inverse seconds. Now, the problem with this is that we're only looking at one reactant here. I'm looking at the time, but I'm only looking at the change in concentration of the butyl chloride. When you have a more complicated reaction and you need to look at both reactants to determine the reaction rate, you're going to need to write a rate law. Now, one can gain information about the rate of reaction by looking at how the rate changes with the changes in the concentration of your reactants. A rate law shows the relationship between the reaction rate and the concentration. Now, there's exponents in the rate law, and the exponents tell you the order of the reaction. How is the reaction occurring in order with respect to each reactant? Now, a standard rate law would look like this. You have your rate. This is how quickly that reaction's occurring. That's what we just calculated before. Now you have this K. That's a rate constant. It is usually given to you unless you're asked to solve for it. But you're given the rate constant, and then you're given the concentration of your first reactant, and we'll call that A here. Now you also have to look at the order with respect to this reactant. M represents the order. Now, you're also looking at the concentration of your second reactant. We'll call that B, and we'll call the order here N. Now, if we were looking at the butyl chloride example, the rate would equal the rate constant times the molarity of the butyl chloride Now, I don't know the order of how this reaction occurs, so I'll just write that as M, and then the concentration of water, running out of room here. And I don't know the order either here, so I would just put that as N. So the overall order of the reaction would equal the sum of the orders, M plus N, and that would equal your overall order. Now, it's kind of hard to understand this when you're not putting numbers to it. So in future videos, I will be showing you the math behind kinetics. It can get a little bit tricky. You have to be comfortable with logarithms and exponents, but in future videos, I'll show you how to do calculate the order of a reaction, write the rate law, and calculate orders that calculate rate reactions that occur at first and second order. I hope this helped you to understand kinetics. It was just a brief introduction. More videos to come.